Hi there. This is a video just to show how to draw or create a free body diagram, graphically analyze these forces or that are present in this situation, and then go on to calculate the forces using Stein rule as appropriate for triangle forces. So we've got a 10 kg mass suspended by two cables, or three cables if you count the vertical one. They're at 40 degrees and 80 degrees to the horizontal, and we can assume that this is drawn to scale, or we can decide that we need to construct our triangle based on working out the angles, and it's probably safer to work out the angles because there's a chance that whoever drew this, in this case I did, and it is accurate, but it might not be, and therefore you have a greater degree of error. So if we're going to draw a free body diagram, it doesn't really need to be accurate. All we're really wanting to do is demonstrate what's going on here, because this is the point that we're interested in. We're not interested in these points. We might if we were thinking about reactions, but we're not. So in this case, what we're interested in is the forces in these two cables, and we know the force that's going to be in this one. So to start with, if we say 10 kgs times G is going to be 98.1 newtons, and we'll probably forget about the 1, particularly in the graphical situation, because we can't measure to 0.1 with a rule. Okay, so if we draw it to create our free body diagram, we need a vertical line, and I'm just going to extend this up a little bit so that I've got something to work with, and that's I'll call it 98 newtons downwards. Then, looking at what we've got here, this must be at 10 degrees to the vertical, because it's 80 degrees, 90 degrees would be perpendicular. So we need to draw an angle in here that's 10 degrees to the vertical, and if we look at this, we've got 40 and 80 is 120, so therefore this must be 60 degrees in here. And that means that we must have, this must be at 50 degrees, because that would be, yeah, there's 10 degrees there, so that must be at 50 degrees. And we can label these. We'll call this 1, this one 2, and 3. Use whatever labeling you like. It doesn't really matter so long as you understand your system. Okay, so that's force 1, that's force 2, and that's force 3. And we'll label it our free body diagram. And we also need some angles to fully define it. So if that's 10 degrees, well then this has got to be 170. This one here, if we say that that's going to be 40 degrees to the horizontal plus 90, so that must be 130 degrees. We don't really need the third one, but we'll do it anyway, and that's going to be 60 degrees because 130, 170 is 300. So we've now got 60 degrees in here. So that's the free body diagram finished, and they're always useful, particularly in a more complicated situation when you're looking at different sets of forces. So in this situation, there's only three vectors to worry about. If you look at a truss later on, there will be many. So breaking them out into the actual joint that you're interested in, or the situation here, that's a good thing to do. Right, so if we draw a vertical line, and because we're going to do this with the set square, with a protractor, it doesn't really matter if this is vertical or not. It just has to be a straight line that's representing the force number 1, which is 98 newtons. So if we measure that out, we've now got so 98.1. I'm not quite long enough. And obviously we can't put the part 0.1 in. So that's 98 newtons, and it's pulling downwards in tension. Okay, so then we've got this force here at 130 degrees. So if we go around to 2, so stick our protractor on here. It's probably a good idea to increase the length of this line so that the protractor can be used as accurate as possible. So 130. We know the sense, but we don't know the length where it intersects. And then if we draw from the top, 10 degrees, just to check, if I put my set square on here, just in case my maths has been a bit crook, transfer it over to there. Yep, it looks the same. So, and over to here, because this is accurate, it's the same there too. Right, so that's our point of intersection. This force is going to be heading up this way, and this one will be heading up that way because they must all connect. And then we can measure off of here. So the scale of this is really a bit on the small side for accuracy. But we'll call that 19, I think. And a force diagram scale equals 1 millimeter equals 1 Newton, and that means that that's 19 newtons. So we'll just write these down here. So forces 1 equals 98.1 newtons, 2 equals 19 newtons, because 1 newton equals 1 millimeter, and they're measuring here. So that's 90, what is it, 88? Yeah. Yep. 3 equals 88 newtons. Okay, so that's it, the graphical part of it done. That extra time made a bit of a mess of my label, but never mind. So calculating, we would use sine rule. So So we go, the sine rule is A over sine A equals B over sine B equals C over sine C. And we could draw another little triangle, but we'll just label this one up for the purpose of this. And we need to know what the internal angles are in the triangle. So that's 10 degrees. And this one here is, well, we decide it's 50 degrees, isn't it? And so that's 60, therefore this has got to be 120. And this vector is A. It doesn't really matter how you label it, but as long as you're consistent, which means that the 120 is, that's the A, the angle that relates to it, because it's the opposite angle to the leg on the triangle. If this is B, then this leg is B, and then that must leave C, and the 50 degrees is the C. Okay, so they correspond with each other. So hopefully that makes sense. So to find B, we can use the first part of the sine rule, and we'll just start from here and transpose it for B. So that means that B, the sine B goes to the top, equals A sine B over sine A. And writing it out fully, so that means 98.1 times sine, and B is 10, over sine 120 equals, so 98.1 sine 10 degrees equals, oh yeah, keyed that incorrectly, 98.1 sine 10 degrees equals, and then divide that by 120, sine 120, equals 19.6 newtons. Well, 19.6, not too far off. You'd expect with a little triangle to have a bit of error. And then looking at C, which is this larger one, which we think is 88 newtons based on our graphical, we would say, okay, so we say A over sine A equals C over sine C. Therefore, C is equal to A sine C over sine A equals 98.1 sine 50 over sine 120 equals, so 98.1 sine 50 equals, divided by sine 120 equals 86.77, or 86.8 newtons, and we had 88 there. So they're near enough to say that we're probably correct. Near enough in that regard. More accurate here. Yeah, so that's the process. Hopefully that's useful. Yeah, and this also applies to several other situations that we'll work through. Cheers.